Hello, gentlemen and ladies. Welcome to another episode of Calculus Fun Times. I, for some reason, had a hiccup, which was the greatest way to start a video. Okay, come on. This is mostly just me messing with a pen. So, hey, just as a reminder, we are working on doing some integrating across regions other than rectangles. And these, I would say, are the I'm going to move my mic down a little bit. These, I would say, are the more difficult examples, so we're going to have to be a little slow and careful as to what we do. So I'm always going to draw them out and what they look like. So the first thing I notice is that y is going from the square root of x to the negative square root of x, and then x is going from 1 to 4. So let me draw what this looks like. 1, 2, 3, 4. So this is not spaced all that perfectly, but that's okay. Oh, and I've got a negative square root of x, so I need to actually redo this whole thing. Just a second. Because I need to be able to see both ends, right? Not straight. I always love it when I do this. 1, 2, 3, 4, 4. And then noticing that we have a square root, the square root of 4 is 2, so the biggest this is going to get is 2. And negative 2. So let me sketch in here. So at 1, the square root of x is 1. At 4, it's 2. And if you remember, it has a nice sort of curve to it. Ugh, I hate how that looks. The first curve was better. Darn it. Oh well. So this is y equals the square root of x. And then the same thing for the negative. It's just take the square root and then negative it. So be careful with that. It should look relatively the same. So that's how that looks. So the area we're going to be integrating over is the stuff in between these two. So this area here, voila. Okay. So if we were to draw in what it looks like in the y direction, we're going from here to here, and then in the x direction from 1 to 4, just so you get an idea of what's happening. All right, let's integrate this. So I'm going to ignore the y bounds for now. They're just going to come along for the ride. Or sorry, the x bounds. I forgot x was on the outside with this one. I'm going to integrate with respect to y. So since this has an x in it, I'm going to treat it as a constant. So I'll get 1 over x times just y, evaluated from the negative square root of x, to the square root of x, and then dx on the outside. So what's nice about this one is, in the end, I am going to end up with something that will only have x's in it for when I go to do my x integral. Let's go ahead and integrate that. Or sorry, evaluate. We already integrated. So going from 1 to 4, and then I'll integrate with respect to x. So I'll have 1 over x times the square root of x minus 1 over x times the negative square root of x dx. Pen's working nice today. Now that I've said that, it's for sure going to screw up. So this is the square root of x over x minus a minus, that's a plus, square root of x over x. Oh, I have two of the same thing. Awesome. Okay. So I really have two square roots of x over x. And I should be able to reduce this, because this is x to the 1/2, and this is minus x to the negative 1. Oh, okay. So, hold on. I'm just going to make this easier. Pull the 2 out. So we're going to think of this as x to the 1/2, and then down here I have just x dx. If you remember your rules for powers, 2, 1 to 4, I'm going to run out of room. So this is going to be the same as x to the 1/2 minus 1, because that's how exponents work. So 2 integral from 1 to 4, x to the negative 1/2 dx. Could I have done this and taken up less space? Probably. It'll be all right. Okay, people, let's integrate. So we're going to add 1 to the power and divide by it. I'm going to cheat and erase one of these steps, so I have somewhere to go with this. So add 1 to the power and divide by it, so that will be 2. 1/2 plus 1 will give me positive 1/2. Dividing by 1/2 is the same as multiplying by a 2, evaluated from 1 to 4. I'm going to take this up here, which is a total cheat move. Oops. 1 to 4. So this is, remember, 1/2 is the same as a square root, so 4 square roots of 4 minus 4 square roots of 1. Square root of 4 is 2, square root of 1 is 1, so this is 4 times 2, which is 8, minus 4, which totally gives you 4. Not what you expected when you looked at this guy, right? It's all curvy and stuff. Kind of crazy. Let's do another one. I'm sorry that went so roundabout. It's because I write enormous. I need to work on that. Let's do a graph. Now, I'm always doing the graph because I want to make sure I know who's who. See, we're going from 0 to 2. These are all positive, so this one I can definitely draw just the positive quadrant. So x, is it x? Yep, x goes from 0 to 2. 1, 2. Do I need my y to be that big? I don't know. We'll find out. And then x squared, when you get out to 2, is going to be 4. Let me erase this line and move it over a little so it's a little more even. There we go. So 1, 2, 3, 4. Oh, and 2x times, yeah, when x is 2 will also be 4. So these are going to share the points 0, 0, and 1, 4. Or sorry, 2, 4. Let's draw the bottom one in red. So x squared, when you're 1, it's 1. When you're 2, it's 4, and it needs to be curved because it's a parabola. So this is y equals x squared. And then I'll do blue on top. There we go. So 2x is just the slope 2. So at 1, it's 2, and at 2, it's 4. And this should be a straight line. Oh, so it's like this little eyelet shape in between. Purple, because red and blue makes purple. So it's flat on one side and curved on the other. That's kind of cute. Kind of like it. Also, purple Easter colors. Let's integrate. So we're doing the volume above this shape. So let's see. Just going to leave the outside integral alone. Put a line here so I don't accidentally cross this guy. And then we're integrating with respect to y. So 4xy plus 2y because, well, y to the 0 power on both these, add 1 to the power and divide by it. Evaluated from x squared to 2x. This one's weird. Kind of like it though. Dx. Ooh, this is going to look rough, but hopefully it combines nicely. So let's see. Integral from 0 to 2. 4x, and then y is going to be 2x, so 4x times 2x, I can do that in my head. So I'm putting in 2x for y, so 4x times 2x will give me 8x squared. 2 times 2x will give me 4x minus, I'm going to use parentheses here so I don't miss any negatives. So I'm going to put in x squared for y, so that'll give me a 4x cubed. X squared for y plus a 2x squared dx. So if we want at this stage, we should distribute this negative and combine some stuff before we integrate. Integration from 0 to 2. Let's see, we have 8x squareds and we lose 2 of them over here because that's going to be a subtraction. So that'll give us 6x squared minus 4x cubed. Ooh, and I almost missed the plus 4x. Okay, so we only had a little bit of reduction. I'm okay with it though. Let's do our integration. So we're going to add 1 to the power and divide by it. So 6x squared over, oh no wait, I forgot to add. 6x cubed over 3 minus 4x to the 4th over 4. Gee, I wonder if I picked these constants so it would do this. I did. 4x squared over 2, evaluated from 0 to 2. So this is going to reduce to 2x cubed minus x to the 4th. That x looks weird. Why did I start writing the weird way? I don't know. Plus 2x squared, evaluated from 0 to 2. Now it's nice because these all have x's that when we put in 0, we're just going to get a string of zeros. So we only have to worry about the 2. So 2 times 2 cubed minus 2 to the 4th plus 2 times 2 squared minus a big pile of zeros. What's nice is these are actually the same, so they cancel each other. So I really only have to calculate this guy. 2 squared is 4 times 2 gives me a lovely 8. Wait a minute. Did I just get 2 8s in a row? Why do I feel like the last one was wrong? 4 times 2 minus 4. Oh, I got 4. Ha! Okay. Sorry, for a second there I thought I was up to no good. As usual. Yep. Good times. Hold on a second. I need to crack my knuckles because my hand hurt. And we're back. And I'm scrolling the wrong way. Oh, today is good. Okay, rewrite as the integral in order which we change the integration and switch the integral. Okay, so this is just for fun. If we do this correctly, we should get the same answer as the previous one because you'll notice that this is the same one as number 11. We're just going to change the order of integration. So, first things up, we want to do this Hold on, erasey, erasey. Come on, eraser, there we go. We want to do this from something to something, 4x plus 2, and I want to do dx first and then dy. So one thing that's crucial with this is that, well, when we looked at our bounds for this first integration, they match these functions. So y equals 2x and y equals x squared. So what we're going to have to do is we're actually going to have to solve this in terms of x first, not y, because they need to match the bounds. So previously we had done dy, which is why these were functions of y, and now I need them as functions of x. So I'm just going to solve for x. So y over 2 equals x, and I'll just take the square root. So square root of y equals x. So all I did was solve for x. That square root is hideous. Oh well. I just don't like it. All right. Now, something crucially important, and I'm going to scroll back to my picture for a second for you to see this, is that the reason why it was going from x squared to 2x was we were doing this vertically, which means the bottom function was this one and the top function was this one. So you do bottom minus top. I'm going to erase that for a second and go back to where I started. Back, 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 back. Now we're doing from left to right. So I need to go this way, which means the blue function, which is 2x, is the one on the left, and the top, sorry, was the red function, sorry, let me write on here, left, and then this top function is the right. Now we talked about this in a previous theorem, and it was on page, it was between 6.68 and 6.67. It doesn't have a page number, sorry. And it was the double integrals over variable regions theorem, where we talked about how, hey, when it comes to the x direction, you go bottom to top, and then with the y direction, you go from left to right. So my left function is going to be the one that's on the bottom-ish, kind of. Or rather, like, it goes here, y over 2. And then my right function will be this one on top, so square roots of y. Now, you also need to change your bounds in the in the y direction. So the x was second and went from 0 to 2 here, and now I'm going to be going in the y direction, so I'm going to go from 0 to 4. So you just kind of flip everything. Hopefully that makes sense to you. Now, I'm not going to lie to you. Usually when it comes to your choice of which direction to integrate, one of these two is easier than the other. Oh boy. And honestly, I think this one is the hard one. Let's get to it. So, we're integrating with respect to x. 0 to 4 stays along for the ride. So add 1 to the power and divide by it. So instead of 4x, I'm going to add this and get x squared. And then I'll divide the 4 by 2 and get a 2. I'm trying to save room. And then 2x. Evaluated from y over 2 to the square root of y, and then a dy on the outside. Let's roll this up a little. Now, I'm going to have to do quite a bit of simplifying in this next step, so try to bear with me. Here we go. I believe in you. 0 to 4, that's not going to change, and now I need to put in my y's. So I'm going to do 2, and then I'm going to put in square roots of y into x squared, plus 2 square roots of y, minus, and I'm going to use parentheses here so I don't lose any negatives, 2 y over 2, ooh, that y looks ugly, squared, why do I keep talking about how they're ugly or pretty? Y over 2, okay. dy. I really need to simplify this. There's stuff everywhere. Okay, so square root of a square, that's going to be fine. That'll just give me a 2y. Plus 2 square roots of y. There's nothing I can do to fix that one. This next pile, though, oh doozies. Okay, so we'll square y and get y squared. And we'll square the 2 to get 4, and then times the 2. So it ends up y squared over 2. And then carry along your negative. 2y2, y. dy. I'm going to combine these two. Integral from 0 to 4, y plus 2. I'm going to write y to the 1/2 because I'm going to have to do the power rule to this in a second instead of square root of y, minus y squared over 2. to y. Okay, let's integrate that with respect to y. I'm going to go all the way over here so that hopefully this will have a prayer of fitting. Nope, no integral from 0 to 4 because we are at the integration step. Let's do this. Okay, square over 2 plus a 2. Add 1 to the power. Y to the 1/2 now becomes y to the 3/2. Divide by a fraction, which is the same as invert and multiply. Move this 2 over. Why does it still want to erase? I don't know. It's having a day. So 2/3 times. So that's going to end up 4/3. It'll be beautiful. Minus y cubed, and then divide by that power. Since there was already a 2 down there, when we add in that 3, we get a 6. Evaluated from 0 to 4. Now the beautiful part is 0, everybody's got a y, which means a bunch of nothings are going to happen. Beautimous. I just have to worry about that 4. So 4 squared over 2 plus 4/3. Hopefully you remember that's from the 2 times the 2. I hope you guys are listening to this with the sound on. 4 to the 3/2. Luckily, halves, remember that's just a square root, so we're going to square root the 4 and get a 2, and then cube it. Hopefully you remember that. If not, hopefully I reminded you. 4 cubed over 6. Whew, let's pull out some calculators because, oh boy, am I feeling like this one's going to be rough. Okay, so 4 squared is 16 divided by 2 will give me an 8. And then this one, I talked about this. So remember, the 1/2 power do get first. So then you're essentially doing the square root of 4, which is 2. And then we cube it. So 2 times 2 times 2 is 8 times the 4. Will give you 32/3. Ew. I was really hoping this came out better. I was wrong. Oh, that makes me sad. Okay, and then 4 cubed I can't do in my head, so I'm totally just going to steal a calculator for a second and calculate that. That's 64. I could have done that because it's 4 times 4 times 4. Why didn't I even try? Judgment. Divided by 6 is 64. Oh, 64 over 6. Isn't that the same as 32 over 3? It is. Beautiful. No, wait. Are those the same? Hold on. 64, when you divide it in half, is 32. Yeah, these are the same. Cool, these two undo each other. You get 8. Why are so many of my problems coming out 8? I almost feel like I wrote this wrong. Oh, it should be 8 because the previous one was 8 and they should match. These should be the same because they're doing the same volume. I need to drink more coffee and maybe talk to another human being other than my husband. Yep, that quarantine is getting to me. Okay, let's do another one. Honestly, this next one's my favorite. I'm not supposed to have favorites, but I do. And the reason this one is my favorite is because I love circles. So, I don't know if this is easy for you to recognize, but this is actually the half circle over the half circle. If you're somebody who's really uncomfortable with graphing, I'm sorry, I had to do a circle. Whee! So this is actually the circle radius 2. Should have done purple. It's hard to see, but it's okay. I have a plan here. So the upper half, that's y equals the square root of 4 minus x squared. Notice if you solve this for 4, I know that sounds weird, that gives you 4 equals x squared plus y squared, which is how I know this is the circle radius too. And then the lower half, this guy, is y equals the negative square root of 4 minus 2. Woohoo! I like that better. Which if you also solve gives you 4 x squared plus y squared. Good times. So we're doing this area, and we're doing, you know, the volume above it from 0 to 2, so this should be a cylinder. Let's calculate this. Green, because I haven't done green yet today. Oh boy. So, y first. Good times. So just hang out x. We're chill. Oh, there's no y's here, so I'm just going to do add 1 to the power, which gives me an y. Evaluated from that thing to that thing. I'm real worried I'm not going to be able to fit this under here. I'm not. Oops, I put a plus sign. Try tiny, it'll make it easier. It doesn't make it easier to see. Dx, because that's the one I haven't done yet. Violent thoughts about that dx. It was nasty. Okay, I'm definitely going to need to write this down here. 0 to 2, 6x square roots of 4 minus x squared minus 6x, another minus, so plus, square roots of 4 minus x squared. So hopefully you notice I have the same thing twice, so I really have 12. So I have 6 of this, 6 of that, 12, this integral from 0 to 2, x square root of 4x, sorry, not 4x, 4 minus x squared dx. I worry about those of you who are watching this on your phone and your ability to read this. You! No, just kidding, not you. You should recognize this if I have a function underneath something whose derivative also shows up. I'm going to need a substitution. Let's use w. Now I'm using w because x and y have both already been used, and I know z is like my third dimension kind of popping out of the paper going from 0 to 2. So I need wubble to w. I've been talking to my nieces a lot and it shows sometimes, so that I can do my integration in peace. Let's go 4 minus x squared. dw will then be negative 2x dx. So we'll divide by a negative 2 on both sides to get 2x by itself. The x and the dx together will make my dw over negative 2, and I'll take that negative 2 out front. And then the inside part here will just end up being where it goes. Now I'm not going to change my bounds, I'm just going to leave them off, because I don't feel like doing it today. So 12 over negative 2, integration, leaving them off. My x and dx get used up making my dw. Negative 2 is coming from the dw. I have the square root of w, dw. It's been a long time since you did these. Oh boy. Yep. Do I want to change my bounds? I kind of do, but I kind of don't. I like them when they change. No, I'm the only one who likes that. We've been over that. You guys don't like it. Okay, let's integrate. So I think this is w to the 1/2. Put that negative 6 out there. So add 1 to the power. So 1/2 plus 1 will give me 3/2. And then divide by 3/2. So that's going to be the same as inverting 3/2 into 2/3 and multiplying. So I'll just shove a 2/3 in here. That should work, right? It thinks I'm erasing for some reason. Fractions. Love them. Evaluated at something. Let me clean this up. So 6 divided by 3 will give me a 2, so this is negative 4. W, which we know to be 4 minus x squared to the 3/2. And I meant to change colors back to green because I'm now on the green stuff now. Let's change this. Going back to x. That's what we're up to. So 2, we already said that, negative 4. What's w? Well, w was 4 minus x squared. 3, 2. Evaluated from 0 to 2. Let's get this party started. This evaluation is going to take me a bit, so we'll go all the way to the left. Negative 4, 4 minus 2 squared. Oh, that's nice. That's going to be nothing. To the 3 over 2. Minus negative 4, so plus 4 minus 0 squared to the 3 over 2. Oh, I'm liking this. Okay, 4, 4, nothing. Because 2 squared is 4, 4 minus 4, nothing. So the first term is 0, plus 4 times 4 to the 3/2. So hopefully you know to do the half root first. Sorry, the half power first, which gives you a square root of 4, which will just be a 2. So I have 4 times 2 cubed. 2 cubed is 8. And then we do, 2 cubed is 8. Wow, I'm slow today. And then we do 8 times 4 to get 32. Now this comes out nice, which is shocking considering where it came from. Were you expecting something terrible? Too bad. I don't know what else to say to you. Area. Oh no, wait. Volume. I totally just said the wrong thing right there. Oh, judgment increasing. Let's do one more funky shape because I want to do one with logs in it to get you guys ready for logs. It's been a long time since we sawed some logs. Math joke, check. Yeah, and then we'll do the hard example. Oh, it's not going to let me fit this in here. Can I just do that and my pen will go away? Perfect. Okay, so let's draw this one so I have some idea what it looks like. So I go from 0 to the natural log of 3 times 2. You totally love this one, right? So you're going to hate me for this, but I'm going to do my scale as the square root of the natural log of 3, and then 2 square roots of natural log of 3 in the other direction. Please don't say Ellen. It makes me judge you. Okay, why? Why am I doing this? And why am I doing it in the wrong color? Okay, because this first one, it goes from x is y over 2 to x is the natural log of 3. Well, x is the natural log of 3 is just this line. It's a vertical line, which is kind of nice. Red. And then the other one is the line x equals y over 2. So you could do it as x equals y over 2, or you could think of it as 2x equals y, which is how I'm going to graph it. So that goes through 0, and then when x is the natural log of 3, it's double that, which is why I did my scale kind of weird. Whee! So it's the area between these two. You like? And then we integrate the function over top of it to make the volume. All right, let's do some integration. I feel like some of you are looking at this and getting mad at me. Why? I can't even see you. It's fine. It's because the bounds I picked were horrible. It's okay. All right, e to the x squared. Now remember, we're integrating with respect to x first. That's totally not going to work, because this is not something we can integrate with respect to x. But that's okay. I know how to fix this. We're just going to rewrite it. So instead, we'll do e to the x squared dy dx. And this is exactly why I taught you this ahead of time. Sometimes the thing you're trying to integrate is wicked horrible, and then you just switch the bounds and you'll be able to do it. So instead, we're going to go from left to right, so this way, first. I'm going to do the y direction first. So I need my left function first in terms of x. Oh, I already did this. It's right here. 2x. I love it when I anticipate what my intentions are, but yet somehow don't. And then, hold on a second. Something about this seems wrong. No, I'm good. And then the upper function is just the natural log of 3 for x. Oh, but I need to solve that in terms of y. But there is no y. Oh, there is no y. It's 0. That doesn't seem right. Something's going wrong here. Oh, I can do it the other way. Okay, so I'm going to cheat a little here. This triangle is the same as this triangle, so I'll just do this one instead. So we'll go from 0 to that line. This is also a sneaky move you can pull. Yeah, I like that better. And then in the y direction, we'll go from the line. No, in the y direction, we go that way, and that means in the x direction, we go along this edge from left to right, which is from 0 to natural log of 3. Yeah, we're good. Oh, that is so much easier to do. Just watch. Square root natural log of 3. Good times. All right, so here we go. 0 to the square root of the natural log of 3. Add 1 to the power, so e to the x squared. Y, evaluated from 0 to 2x. What's nice is when this is 0, that'll go away. Dx. So when I put in 2x for y, I'll get 2x for y, e to the x squared, oh yeah, dx. So I'm going to hop this 2 out front. Or do I need to? No, I don't need to. Okay, hopefully, right about now, this one's tricky. You see that I have a function and its derivative appearing, and you're like, ooh, I can substitute. W is x squared, and then dw will be 2x dx. Fantastic, because I derive this, move the power up front, subtract 1. These together will make my dw, and then my w will be in the upper part. So I'm not going to change my bounds again, because you guys don't like that. E to the w, dw. That's like the easiest one I've done in a long time. That's just e to the w, evaluated at something. Let's change back into the red junk. So I'm going to substitute back in e to the x squared, and the bounds for this were 0 to the square root of natural log of 3. Let's shove that stuff in. E of the natural log of 3 square root squared minus e to the 0. Oh boy. So, couple things. Roll it up. Square root of a square will be absolute value of the natural log of 3, but natural logs can't, or well, this natural log, it was bigger than 1, so it'll be positive, so I don't need to do that. Minus e to the 0, which is just 1. And then the natural log of 3, and then eing it is just 3, because those two undo each other. They're inverse functions. So we get 2. Bet you didn't see that coming, because, you know, it's a 2. Hopefully you followed along okay with this one. I would say, honestly, this is like a 4-star problem. It's like a general. It's, you know, the hardest one I've done so far. I think the one I do next is much easier, but, you know, different things for different people. Let's do a more practical and applicable problem. But this one's just as long. And there's lots of B's. So your company is planning a new line of compact cars at between $10,000 and $15,000 for its price. The marketing department reports that the company's prices of cars at P dollars per car. The demand will be between Q equals the following and P equals the following in the first year. What is the average of all the possible values of your company revenue could expect to earn in the first year? Oh boy. So let's start out with graphing this. Now I'm not going to lie, I use technology to graph this because it gets real gross real quick, because that's who I am. So I know I want a price between 10,000 and 15,000, not to scale. And that when I put those prices into my two quantity functions, I get the following. So I'm going to go up by 5,000. 5,000, 10,000, 15,000. I think that's as hard as it gets. Woohoo. So I'm graphing price versus quantity here, in case that was unclear, and trying to get the revenue. So when I'm at 10,000, this first pricing function will be 20,000 minus 10,000, which will give me, oh, these are supposed to be in thousands, not in hundreds. Let's add a 0 in here so that this makes sense. If you can't laugh at yourself. And then when it's 15,000, it'll be 5,000. So this is that first function. Q, my Q's are gross, equals 20,000 minus P. And let's graph the second one so we can see who's on top and who's on bottom. So when it's 10,000, this will be, oh, it'll be 15,000. That's why I needed to go up that high. And then at 15,000, it'll be 10,000. Oh, so they're nice and parallel. Oh, that's kind of cute. Okay, I like it. I like it a lot. I'm hoping I gave you guys enough room for this problem. So we're doing this little square box area in here. I meant to do that in blue. I'm loving the Easter pastels. It's super cute. Okay, I want to do my integral in a different color, purple. All right, so I need to set this up. Average possible revenue. So one thing that's important is we're going to be doing average value for this. Yeah. Average of the revenue. So I need to think about revenue. Revenue will be whatever price you have times the quantity you sell. So that's going to be the function that I'm going to be looking at this. But then I'm also going to be averaging. So because of that, I have to average across the possible values for the revenue. So one thing that's hard about that is that means I'm averaging across the area. So I'm going to be doing, I should use R for this. Sorry. We'll call it R. So I'm going to be doing R bar. Yes, I did that on purpose. So that'll be 1 over R, the double integral, PQ, to do the volume, and then dividing by the area. Oh boy. So this is going to go from, let's see, do I want to do it in the P direction or the Q direction? Let's do Q first. So if I'm doing it in the Q direction, I go from bottom to top. Yeah. So dQ, dP. Do I want to do it that way? Yeah, because then my p-values are right here. So that'll go from 10,000 to 20,000. Or sorry, 15,000. So I'm figuring out my bounds that go with this, because that'll be easier. And then my q's go from in the Q direction, which is my Y direction, so it's got to go from bottom to top. So the bottom is the red function, top is the blue function. So that'll go from 20,000 minus P, oh, this looks horrible, to 25,000 minus P. I'm sorry for the giggling. I'm sure that comes off as loud on the video. I should be a professional and control myself, but then I wouldn't be myself. Okay, so you're hopefully looking at it and thinking, oh, that's not too bad. It's just got a lot of stuff. And if you're wondering what R is, I'm going to do that in a minute. It's just the area of this guy. So I'm hoping you notice you can think of this as like two rectangles. So, or sorry, two triangles. Two triangles, they have the same, let's do area, base times height. So the base width is the distance from 10,000 to 15,000, which is 5,000, times the height. So they both are going to have the same height. That's this distance or this distance. And this one I think is the easiest one to see. It goes from 5,000, it should have been 5,000, not 50,000, to 10,000, which is only 5,000. Or you could do it this direction, which is 10,000 to 15,000, which is 5,000 also. So I get 1/2 times 2, which is just 1, and then 5,000 times 5,000, which is just 5,000 squared. So I'm going to divide by that in the end because that's a huge number. All right, we'll just leave it as 1 over R out front for a second. Area of R is going to be our R over here. Okay, cool. Let's integrate. So I'm doing the inside one first. I'm going to take the 10,000 and 15,000 for a walk. I'm integrating with respect to Q first. So I'm going to add 1 to Q's power and divide by that. So I'll get P Q squared over 2. And then I'm going to evaluate that from 20,000 minus P to 25,000 minus P. It'll be okay. I believe in you. To P. So remember, in the end, we're going to be integrating again with respect to P. So this will get clearer as we go. All right, let's do some substituting. So don't forget your 1 over R. It's coming along. Don't forget your integral that you haven't done yet. Is this going to fit, you think? It's funny how I'm talking to no one. Okay, so I've got P over 2. 25,000 minus P squared minus P over 2. Actually, I could factor out the P over 2. Let's do that, because I bet you these simplify and combine a little bit. Erase. Dunk, dunk, dunk. Nope, still erasing. Dunk, dunk, dunk. 20,000 minus P squared to P. Yeah, I totally want to do it that way. Because then I can just FOIL these out and simplify some stuff, and I bet you some things cancel and make it easier, and then I can multiply by the P over 2, and that'll make a much nicer function to integrate. The problem is I gotta FOIL these huge numbers now. Oh boy. Self-judgment increasing. 1 over R. See why I left so much space for this one? It's like I knew. Don't forget your P over 2. Just carrying those along. Now I'm going to multiply. Yonk. So, you guys cool with me just writing this first part as 25,000 squared, and I'll calculate it later, and then I'll get negative P times that times negative P, so I'll get negative P and then 2 25,000, so this will be 50,000 P's plus P squared minus 20,000 squared, whatever that is, minus, so you got to really watch our minus signs on this, so this is going to be negative, negative, this will be a plus. Actually, let's just go ahead and do that now. Plus 20,000 times P, and then P times 20,000, so I'll get 40,000 P's. And then negative P times negative P will be positive P squared, then a negative, so minus P squared. Okay, dP. I want to do a little bit of highlighting here so you can see what happens. So the positive P squared, that totally didn't work. And the negative P squared will undo each other. And then I'm going to combine these guys and combine these guys. And I think I'm going to do that off camera so that, you know, this is simpler when you look back at it. I believe in my heart of hearts this is something you can easily calculate though, so you shouldn't have such a hard time with this, hopefully. 1 over R. 10,000. 15,000. P over 2. And when the smoke clears, you will have 25,000 squared minus 20,000 squared, which is 225,000, minus 10,000 P's. To P. You get 10,000 because negative 10,000 because negative 50,000 plus 40,000, negative 10,000. Okay, let's do our last bit of cleanup before we integrate. So I'm going to do one little sneaky move here. I'm going to pull the 1/2 out front, so I have 1 over 2r, 10,000, 15,000. Now I'm just going to distribute the p. Oops, I missed a 2. Oh, I should have just divided by 2. That would have been easier. Screw the moving the 1/2 out front. I'm going to distribute now. So I don't know what that divided by 2 is. Hopefully it's nice. 2, 2, 5, 1, 2, 3 divided by 2. Oh, that's cute. Why am I calling numbers cute? 112,500 minus 5,000. Cute. And then p squared. Perfect. Let's go ahead and integrate. So just a reminder, r is 5,000 squared, so let's just write her in there. Whatever that happens to be. Now we're integrating, so these bounds are going to go away. I'm going to get 11250, add 1 to the power, minus 5,000, add 1 to the power and divide by it. Evaluated from 10,000 to 15,000. I really regret not doing this in thousands, because that would have made this much easier. That'll be okay though, right? Sure, she says as she gets scared. Okay, so you know the drill. I gotta plug in 15,000 and 10,000 and do some subtraction. I don't want to. 12500, 15,000. You might need to do Excel for this because these numbers are so big they might make your calculator crap out. Just saying. Actually, having said that, I'm going to double check my calculation because I'm a little worried that my calculator will not do this. If I remember correctly, I used a bigger program to do it. Oh boy, I have too many parentheses and that looks not like a 1. Oh, not 15,000, this one's 10,000. Minus 5,000 over 3, 10,000 cubed. Did I get all my parentheses? I think I did. Okay. I'm going to double check my calculation and then we'll go. Okay, ladies and gentlemen, if you were calculating with me, you realized I had an error all the way back earlier and I apologize. So I'm going to fix that right now. Right about here, I missed a comma. So it was 1, 2, 3, and then 2 more 0. Actually, let me do that in a different color so it's more noticeable in your notes. So 1, 2, 3, and then 2 more zeros. So my comma should have been here and here, and that's how I ended up with too few zeros. So let's correct that elsewhere. So there should have been 2 more zeros here. Yeah. Is that right? Hold on. Yeah, in the end you end up with 5 zeros. 1, 2, 3, 4, 5. Wow, I am excellent at this. 1, 2, 3, 4, 5. Yep, cool. This was a huge mistake on my part because when you would have calculated this, you would have got negative volume. Which, if you got negative volume, that would be a good indicator that your pricing model is unrealistic and that you should. Yeah, I missed the comma down here. I actually didn't write this number in my notes, so that was awesome on my part. So 3 more zeros here, comma, comma. 3 more zeros here, comma, comma. I hate myself. Anyway, judgment. When you do that, you get the following as your average profit from these cars with this pricing model. So what's interesting about this is, yes, you actually do make a profit on average when you produce this many. So this is an interesting problem because it makes sure that you keep a positive revenue, which is good times, but doesn't account for cost. So at the same time, when you're looking at this pricing model, if you now go look at your costs and it exceeds this on average, then you're in big trouble. Ladies and gentlemen, you should probably adjust your pricing model. And what's kind of fun for this too is it gives you like a range of values for these cars, somewhere between 10,000 and 15,000. If you've ever had to negotiate the price of a car, this tells you, oh, so when they're pricing it, they probably are going to price it at 15,000, then negotiate down and not go below 10,000, which is kind of fun for thinking about how this gets used. And I apologize for the error. I hope you still understood what's going on. That's what I get for calculating and not double checking myself before I wreck myself. See ya in the next one or in office hours. Cats and kittens. Bye.